It lords over the nearby planetary group, a superworld more than twice the mass of the multitude of other planets combined. This turning giant generates perilous radiation, fierce typhoons, and misleading magnetic fields. A spacecraft rushes into the whirlwind, challenging the planet Jupiter to surrender its mysteries. Juno is part of a larger effort to peer into giant Jupiter, uncovering a time long ago when planets were born and destroyed, flung into space or hurled into the sun. It was a period when the fate of our own small and fragile world hung in the balance. The Greeks called him Zeus, the Romans Jupiter, the ruler of the gods. He concealed his evil deeds behind swirling clouds. Only his wife, the goddess Juno, could pierce the veil of mists to catch him in the act. NASA's Juno, the Jupiter Near-Polar Orbiter, left Earth on a mission to probe the enigmatic Jovian atmosphere and uncover clues to the powerful forces that churn beneath its roiling cloud tops. At more than 300 times the mass of Earth, Jupiter contains over 70% of the mass of the solar system beyond the Sun. Juno is the latest in a series of missions designed to measure the planet's properties. How it became so massive and how it shaped a rocky blue world like Earth. To understand Jupiter's early years, astronomers have been observing another planetary system taking shape in the constellation Pictor, 63.4 light-years away. A young star, Beta Pictoris, is growing its first crop of planets. One is large enough and distant enough from the star to be photographed. Beta Pictoris b. Astronomers have now seen it on both sides of its orbit. Looking at Beta Pictoris, you glimpse a snapshot of our solar system as it might have been billions of years ago. The observed planet is forming within the outer zone of dust storms, gas, ice, and countless small objects called planetesimals. Matter swirls into it, likely creating a fury of gravitational and magnetic energy similar to that surrounding its distant cousin, Jupiter. Jupiter's magnetic field is 20,000 times stronger than Earth's. If you could see Jupiter's magnetosphere in the night sky from Earth, it would appear wider than the full moon. Jupiter's zone of magnetic influence is so vast that it extends beyond Saturn's orbit, like a lightning bolt flung by Zeus into the outer solar system. This immense magnetic field results from a powerful double dynamo, one deep within the planet and another near the surface that encircles the equator. When Jupiter's moon Io moves through this magnetic field, it emits intense bursts of radio energy, strong enough to be detected on Earth. Volcanic eruptions on Io send streams of charged particles into this field, fueling massive auroras that illuminate the poles of the giant planet. A haze of charged particles races around the planet, forming a radiation belt that exceeds lethal doses for humans by thousands of times. In 1973, Pioneer 10 first detected this radiation belt when it passed within 130,000 kilometers of Jupiter's cloud tops. A year later, Pioneer 11 captured the first close-ups of the Great Red Spot, Jupiter's immense signature storm. The findings from Pioneer informed the design of the twin Voyager spacecraft launched in 1977. Engineers shielded critical components from radiation, enabling Voyager to capture 19,000 images, including new views of Jupiter's ghostly rings, the icy terrains of its moons Europa and Ganymede, and the dynamic volcanoes of its innermost moon Io. The Galileo mission ventured even closer in 1995, returning a wealth of discoveries about Jupiter's atmosphere. With a composition nearly identical to the Sun, Jupiter provides a window into the birth of our solar system, approximately 4.6 billion years ago. Stars and planets form when clouds of gas and dust collapse, often triggered by the explosion of a nearby star. A shock wave from the dying star causes the cloud to contract and spin. As material flows toward its center, temperatures rise, creating a faint protostar. Billions of tiny dust particles collide and stick together, forming sand-like grains called chondrules. Drawn together by gravity and electrostatic forces, these chondrules grow into pebbles, then rocks, and finally planetesimals. These kilometer-scale objects either collide and merge or break apart. Meanwhile, matter continues to flow into the central star. As the star brightens, radiation begins to blow away leftover dust and gas. Beyond a certain distance, called the frost line, temperatures drop enough for water, methane, ammonia, and carbon compounds to form solid crystals. Here, objects of rock and ice rapidly coalesce into protoplanets. The largest protoplanets become the quickest to endure. To survive Jupiter's intense radiation, Juno's electronic circuits were encased in a titanium vault. Its components were made of radiation-hardened materials, and every part of Juno that could be shielded was wrapped in lead foil. Launched on August 5, 2011, Juno was initially called the Jupiter Near-Polar Pioneer. It was the second mission of NASA's New Frontiers program, a series of medium-sized missions designed to expand our knowledge of planetary bodies and provide new insights into the origins of the solar system. The first mission, New Horizons, traveled 9.5 years to the outer solar system, mapping Pluto and its moon Charon. It uncovered clues to their complex and violent history. The third mission, OSIRIS-RX, launched in 2016, visited the asteroid Bennu, collecting rocks to return to Earth. These samples aim to answer fundamental questions about the birth of the solar system and the origins of organic molecules that sparked life on Earth. Each of these missions has tackled daunting technical challenges. For Juno, the challenge was to fly close to Jupiter without being scorched by its powerful radiation belts. To achieve this, the spacecraft followed a series of highly elliptical orbits, skimming Jupiter's poles and dipping beneath its radiation belts. On each 53-day orbit, Juno spends just 2 hours in the zone of maximum danger. The spacecraft spins 3 times per minute, allowing its instruments to capture around 400 slices of data from pole to pole. Beyond photographing the planet's intricate surface features, Juno is conducting a CAT scan of Jupiter. Scientists see structures in the planet's atmosphere akin to Earth's: cyclones, jet streams, and storms, but Jupiter's systems are vastly different. The planet's larger size, faster rotation, and greater distance from the Sun's warmth result in dramatic atmospheric dynamics. Juno's data reveals that Jupiter's surface winds extend as deep as 3,000 kilometers. Below that, magnetic fields slow these flows, enforcing uniform rotation. Deeper still, scientists believe the planet harbors a layer of metallic hydrogen surrounding a solid core of rock and ice. Throughout much of the 20th century, scientists theorized that giant planets like Jupiter formed in distant orbits far from their stars, gathering icy planetesimals. Little since there is less strong food during their early stages, this general comprehension was floored by ongoing exoplanet revelations. The Kepler space missions, alongside ground-based planet-hunting frameworks, have recognized in excess of 2,000 stars with circling universes up until this point. Not many look like our planetary group. The inward circles of many star frameworks are graced with supposed sweltering Jupiters, enormous gas Goliaths the size of Jupiter or larger that whip around their parent stars at short proximity. Some are being deprived of gas by strong solar breezes. Then there's a class of rocky super-Earths, at about 2 times the mass of our home planet. They occupy the deepest circles of numerous other planetary groups. Incidentally, the most widely recognized planets inside these inward locales are not rocky at all. It's a class of gas dwarfs, smaller than Neptune but weighing up to around 10 Earth masses. More modest, Earth-sized planets are, as a matter of fact, uncommon. How did our planetary group develop in such an alternate direction? The response might lie in Jupiter's violent past. As Juno passes near the planet, her path twists due to convergences of mass beneath its surface. Since Jupiter isn't solid, those areas are allowed to move and shift. Jupiter turns faster than any other planet in the solar system, completing a rotation every 9 hours and 55 minutes, which bulges its equator and flattens its poles. By plotting small variations in Juno's timing as it orbits, scientists can detect convergences of mass beneath the surface. What lies beneath Jupiter's surface? How does its density vary? How dynamically does it twist? And how massive or solid is its core? These are clues about when and how it formed. Our planetary group is still buzzing with remnants of its formation, wandering rocks that haven't changed since they formed almost 4.5 billion years ago. Most are so small that when they encounter Earth, they simply burn up in the atmosphere. A few larger ones survive the fall. Scientists date these planetary shards by measuring molecular variations called isotopes of 2 specific metals, tungsten and molybdenum. These meteorites appear to come from two separate populations that formed in the inner and outer solar system. Something likely split these two regions apart, preventing them from mixing. If this great divider was the young Jupiter, it had to have grown very quickly, reaching over 20 times the mass of Earth within the first million years of the Sun's formation. Its gas giant neighbors, Saturn, Uranus, and Neptune, would have formed afterward. By partitioning the solar system in this way, Jupiter would have cut off the flow of material into the inner solar system, stalling the formation of large rocky planets or super-Earths. Then came one of the most dramatic events in the history of our solar system, set into motion by Jupiter's rapid growth. The discovery of large gas planets within the inner regions of other planetary systems has raised new questions. If these giant planets formed beyond the ice line and migrated inward, could Jupiter have followed a similar path? To test this idea, scientists used a supercomputer to simulate the early evolution of our solar system. They input a set of initial conditions into a program designed to model the interactions of gas, dust, gravity, and energy. The simulation takes us to one cold, dusty corner of the universe 4.6 billion years ago. Shockwaves from a supernova blast disturb the cloud, causing it to collapse into a dense central region. Near its center is a massive swirling maelstrom of dust, gas, and water. Matter streams into a newborn star along a thin disk. Within this disk, Jupiter, the first standard planet, forms in the outer reaches, far from the Sun. Within a million years of its birth, Jupiter collects vast amounts of ice and hydrogen gas. It reacts to the gravity of the Sun and the mass of the inner solar system. The model shows Jupiter's inward spiral, known as the grand tack. As the giant planet's orbit shrinks, it destabilizes the inner solar system, ejecting most massive objects into outer orbits or into the Sun. Eventually, Jupiter feels the pull of another growing planet, Saturn, and retreats to the outer solar system. This dramatic migration leaves behind just 20 or 30 small planetary embryos in the inner system. Over the next 50 million years, these embryos interact gravitationally, leading to collisions. By the time the dust settles, only 5 planets remain, including Earth and a Mars-sized world named Theia. All this changed when Earth and Theia collided. A computer model shows the first 24 hours of this event. Theia shears about a third of Earth away. The debris encircles Earth, forming a molten ring. Within a century, this ring cools and coalesces into the Moon. The grand tack hypothesis explains several long-standing mysteries. Why, for example, is Mars so small? The idea is that Jupiter cleared out much of the material that would have otherwise accreted to form a larger Mars. Spacecraft like OSIRIS-RX and Lucy are studying asteroids and other remnants of the early solar system to test these theories. For example, the asteroid Bennu, just 500 meters wide, is a time capsule from 4 billion years ago. At Jupiter itself, the planet's moons, Io, Europa, Ganymede, and Callisto, offer further insights. These icy worlds, some of which may host subsurface oceans, formed late in Jupiter's evolution. Their unique characteristics, along with data from missions like Juno, continue to deepen our understanding of Jupiter's role in shaping our solar system.